All right, great. Yes, so next we have Li-yao Xia, is that?
Yes.
Who's going to tell us about implementing deriving as a library. This is going to be interesting. Thank you. Let's have it for our speaker.
So whereas usually you implement stuff by adding code, here I'm going to propose removing code from GHC. And in particular, I'm proposing to remove the deriving keyword from the language entirely. So what is deriving? Deriving is this thing that lets you construct instances of type classes. So in standard Haskell, deriving supports just a few type classes in the base library. And then there are some extensions that give you access to more type classes. And there are actually quite a lot of these extensions.
Sorry.
And so what I'm saying is that, well, this is way too much. And there are many bad things about this. So first is that if you want to add yet another feature, you have to add a new extension, and then you have to change the compiler again. Also, like these extensions, like they really feel like they've been added like very incrementally. So in a way, if you already know how deriving works, then the next feature may make sense. But if you're new to Haskell, then you have all of this stuff that you just get overwhelmed with. And finally, there's the fact that actually all of these features don't actually do what you want to do. And you run into odd limitations when you try to derive some type classes in particular. Deriving via with traversable is one example of things that just doesn't work. And so what I'm proposing is to simplify the language. It will make the compiler simpler to maintain, and also deriving actually easier to use. And so we can do much more with less. So how do we do this? By taking deriving out of the compiler, and instead we can implement it as a library. And I have implemented a little proof of concept, which is available on GitLab. So I'm going to just give a very brief overview of the kind of stuff you can do with it. So the starting point is to make instances first class. So the idea is to think about what is a type class. So we see a class, and one way to understand it is to know how it's compiled by GHC as a data type, actually. So when you define a class, it's actually some kind of record type in core. But, well, if it were just a record, we wouldn't need the class keyword. So it's a data type, but also there is some implicit parameter voodoo going on that in between the surface and core that lets you insert values of this data type. And so in particular, so one way to view this is that there is some kind of primitive that takes some constraint C in your some implicit context, and it turns it into an actual value that you can use. And then similarly, what is an instance? Well, if you an instance really, well, if a type class is a data type, then an instance is a value of data type. Plus, again, some stuff related to this implicit parameter thing. Okay? And so what deriving does is to construct instances for you. But now that we see that instances are just value, we have a perfectly fine tool to construct values. It's called functional programming.
What about the voodoo?
Well, the idea is that the voodoo is really nothing, right? Yeah, the idea is really to separate the voodoo. Because now the voodoo is like really simple. It's just this instance keyword, and then the rest of this information here is just a value, and so you make the language much simpler in that sense. So how do we derive values by functional programming? So to start, an example of deriving using a new type. So you wrap the int in some MIT, and then you may want to have EQ reuse the EQ instance for int. And so how this works with these first class instances? Well, if you have, now that EQ is a data type, and you have this dict that lets you get access to to the instance as just a value now, well, all you have to do to obtain an ek of my t is to coerce it. And so using only this new primitive that we have for this first class instance variant of type classes. And now via is just coerce. So we can do deriving via without like adding anything to the language. To show another example, one is a generic deriving. And so like whereas deriving via lets you coerce class dictionaries between coercible types. Here you are going to like inspect the structure of a data type, which usually has some sum of product, and you can use that to generate ek instances for most Haskell data type. And you can use deriving via to package this in a somewhat nice way. And so what I'm proposing now is that this instance here that was used for this generically new type that carries this generic ek instance now becomes just some value generic ek, which takes some ek dictionary on the underlying generic representation and constructs the dictionary for the type that you want the new ek instance for. And now once you have this generic ek, well, to derive this instance, you just have to, well, you just put the value here on the instance and you're done. So in particular, generic deriving subsumes the stock deriving, that is the standard Haskell deriving. And so now we see that deriving really is just a polymorphic value, some polymorphic class dictionary. So as I said, it's just functional programming. We already know how to do that. Here's another more fancy thing that you can do using this model. So, looking at, so we are going to need this variant of the functor class, where instead of mapping just functions, you map isomorphisms. And so it's like functor, it's like, actually it's more general than functor because, well, you can now map on the left of an arrow. And the other thing that we will need, notation we will need is this generic class, which gives you an isomorphism between some uniform representation and the generic type that you care about. Now, generic deriving for the IC class before, I had just put some ellipses, and now I'm showing you how we can actually implement that using these primitives. And so, again, you are given some dictionary on the generic representation, and all you need to, and now you want to turn it to an EQ of A. And so what you can do is that you can use the rep to turn the rep A into an A, and use the isomap to do that under the EQ. Okay? And here we make a remark that actually this code barely depends on the fact that this is ek. It only uses the fact that EQ is an instance of this isofunctor class. So we can generalize, right? And in particular, isofunctor can be derived generically, like functor. Like all you have to do is to map something, you pattern match on it, you reuse the same constructor on the right-hand side, and then you fold on the data, and then whenever you see a type variable occurrence, you just apply the isomorphism. Okay, so I'm not going to show the implementation, but so this can be done. So this is just a generalization of isomap to arbitrary generic type constructors F. And so now you generalize it by replacing isomap by this generic isomap, and you get this very general looking thing, but essentially I replace this EQ by some type variable C. And so now this works like for all classes that implement this isofunctor generically. And so this works for quite a lot of classes, but not all of them. So show and read don't have like these kind of this right kind of generic implementation to use this thing. All right, so it's quite powerful, but not all powerful. All right, so now to conclude, I've shown you what we can do by deriving, making deriving as a library. How do we do that? We use instances as first-class values. So there is this library on GitLab that I'm using. There is also a GHC proposal that tries to make this concrete syntax actually part of Haskell. For example, the library uses template Haskell instead of the instance equals syntax that I've shown in these slides. And we can do some neat things like generic deriving of generic deriving. Thank you.
All right. Thank you, Li-yao. Do we have any questions? Oh, yes, we do.
The dict primitive that you showed earlier, how tricky is it to implement this? Like, that seems to be kind of like the thing that makes a lot of this possible. Like, do you have to do any...
Oh, no, that's the easy part.
That's the easy part.
Yeah, the dict thing, you could think of it as like you declare one type class called dict of a data type called C, and its only method is a value of type C.
Oh, okay. So this is sort of like the reflection style
Yes,
trick?
right.
I see. Thank you.
We could probably take one more quick question if that's, yeah, not.
So type classes and instances are not just values. There's also attached type families. Do you have any thought about that? Or are they completely out of this plan?
I think for now, yeah, type families are out of this plan. I think maybe once we have dependent types, there might be a way, but yeah, at the moment, I don't see a way.
Great. All right, let's thank Li-yao again.